All right, hopefully the quiz went well. So let's go over the quiz. That's the best thing to do right away. Okay, so here's your quiz. And what we've got is we have our function f and we have our u 3/5 4/5. Okay, which by the way is a unit vector. You can check that if you want, but it's fine. 3, 4, 5 triangle basically. And the first question is find the gradient of f. So to find the gradient of f, what two things do we have to find? Yeah, we got to find fx and fy. We got to find the two partial derivatives. There's a function of two variables, so it's just two different derivatives. I'm going to leave f there so I can refer to it. So to find the partial derivative of f with respect to x, what do you get?
Y squared minus 2.
Yep, y squared minus 2. And now we got to find the partial derivative with respect to y. And what do you get?
2xy plus 1.
2xy plus 1. And that's the gradient. And I wonder, let me see. Because I wasn't able to do it on the Google, but let's see if this one's got it.
It should be under relationships or operations for the upside down triangle.
Yep, did you find it?
It's an operation.
Yeah, no, but I'm looking at it. I'm not seeing one. Miscellaneous.
No.
Try miscellaneous. Yeah, let's see. Yeah, so there, so we can go grad f equals this guy. And that was part A. Okay, again, you are not responsible for knowing how to find strange symbols, especially on the exam. Do not waste a lot of time looking for strange symbols. Just write it in letters is just fine. And quiz is good. But I figure since I wasn't able to find it in Google, or Canvas does have it. Okay, B. All right, so B is find du of f of xy evaluated at the point -1, 2. Okay, so one of the hardest things about this is just to remember what all this stuff means. Okay, so we got to try and find what does all this mean. And here we have du of f of xy. The way you say that is that's the directional derivative of the function f in the direction of the unit vector u 3/5 4/5, evaluated at the point -1, 2. So one of the hardest things might be is just to kind of get everything straight in terms of what these instructions are telling you. Is that clear? All right, so let's go do that. And remember we had a formula, it was a theorem that we had last time, that said that the directional derivative of a function evaluated at a point, or even directional derivative of a function, is equal to the gradient of that function dotted with the unit vector u. So all I have to do is take the gradient and dot it with 3/5 4/5. So first, we're at the point -1, 2. So first thing is, now I'm going to write grad because this one to type in the letters. Grad of f at -1, 2. Now that just says plug in -1, 2 into our gradient. So y is 2. So 2 squared minus 2 is 2, comma. And here we have 2xy plus 1. 2 times -1 times 2 plus 1 is? This isn't supposed to be hard, it's just arithmetic. So what's 2 times -1 times 2 plus 1?
-3.
Yeah, -3. Again, that's not a trick question there. Okay, so there's our gradient. I guess I should put an equal sign. Any questions on the gradient at the point -1, 2? So now it's very easy. We just find du of fx xy. And since I've got lots of symbols, I think I'm going to go into the editor. So du d sub u of f of x comma y is equal to, well, the formula was, and you said there's one in operations. I see the triangle. I don't see an upside down triangle. Oh, there it is. Yeah, there is one. What do you know? Okay, the gradient of f dotted and of, I'll just go dotted. And I'll just go there. Dotted with u. And remember, the gradient of f was 2, -3. And then we want to dot it with u, which was 3/5, 4/5. And now it's, I mean, you gotta know how to do a dot product, but it's basically arithmetic. That's 6/5 minus 12/5. And hopefully you can all do that in your heads. What do you get?
-6/5.
Yeah, -6/5. Okay, very easy to watch me do. Hopefully it was easy for you to do also. But there's our directional derivative of f in the direction of u evaluated at the point -1, 2. Okay, C. C is really easy if you know what to do. Okay, find the maximal directional derivative of f of x at the point -1, 2. All right. What direction is the maximal directional derivative always in? We had a theorem about it.
Positive x.
Not positive, definitely not positive f. It's a good idea. What's the direction at which the maximal directional derivative always lies in? Remember, we had a theorem. Huh?
U?
Mu?
No, U. Is it U?
Yeah. Now, u is just some kind of arbitrary thing.
Mm.
Okay. It always lies in the gradient. The gradient points in that maximal directional derivative. The gradient points in the steepest possible direction. Do you remember that? And steepest means maximal. So all we have to do is find the directional derivative in the direction of the gradient, but the directional derivative is a gradient dotted with u. So we just have to find, so let me write this out and then I'll talk about it. So we need to find d sub grad f that didn't work. I do have to do this grad f being mean. All right, we'll just go grad f of f. I think it'll show up nice when I save it. We'll see. Well, that's equal to the gradient of f dotted with the unit vector in the direction of the gradient of f. And remember, that is the gradient of f over the magnitude of the gradient of f. But that, if you take the gradient of f and dot it with the gradient of f, you get the square of the magnitude. That's just the magnitude of the gradient of f. And good, it does look good when you hit go. All right, now you don't have to do this proof, you could do it, but I figured I might as well prove it because it makes a lot easier for calculation. But you could just do the directional derivative, but you do have to compute the magnitude of the gradient of f. And that is equal to, well, our gradient of f, okay, at this point was 2 comma negative 3. And what is the magnitude? What's the magnitude of the vector 2 comma negative 3?
Square root of 13.
Yep, square root of 13. So let's pop it in. Square root of 13. And that's it. Okay, square root of 2 squared plus negative 3 squared, which is square root of 13. Okay, you could go work it out with all the arithmetic, but this derivation means you don't have to. It's just the magnitude of the gradient is always the maximal directional derivative. Okay, again, you're not required to do the full proof like I just did. You could just work it out. But you are supposed to remember the theorem that the gradient always points in the direction that has a maximal directional derivative. Okay, so it points in the steepest direction. Any questions at all on the quiz? Any questions? Okay. Easy to do if you know what to do. Impossible to do if you don't know what to do. Sound right?
So I have a question, but it's not related to the quiz.
Sure.
It's related to the homework.
Mm-hmm.
Are we able to use a gradient to find a tangent plane?
Absolutely.
Do you mind showing me real quick? Just a brief example.
Okay. I'll just do it here. I mean, since I'm here right now. Yeah. So let's suppose that we have, I don't know. Let's do this one. Might as well do our function here. What if I did part D? Fine, which I didn't, but just like, you know, had I done it, and I could have, find the equation of the tangent plane at the point -1, 2. Since we're already here, we might as well have done all the work. I might as well do it. Is this kind of what you want to know?
Yeah.
Okay. And when I say the tangent plane, I mean to the function f, which is, maybe I'll do this. Yeah, I think it does weird copy and paste things, so I got to erase a little bit. Okay, so we want to find the tangent plane to this function at the point -1, 2. The idea is I've already done a lot of the work. Okay, I've already found the gradient. But here's what you do, and this is kind of nice, and I'm glad you asked because it's a good thing to know, and I didn't cover it in the book. I don't think covers it either, and it should. Is that we can re-look at this tangent plane as z equal. Let's just do this actually. Okay, so we could look at that tangent plane as that. Let's call it FZ. That's the Z coordinate. And we can rewrite this. We can rewrite this as xy squared minus 2x plus y minus 4 minus z equals 0. Okay, hopefully you understand that was very basic. I didn't do anything too fancy, just subtracted z. You good with that? Now I can find the gradient. And the nice thing is whenever you do this, if you have a function like this, the third coordinate of the gradient in 3 variables is always just -1. Got it? So what we can say is our normal vector is going to be equal to, well, we already found the gradient at that point, which was 2, -3. But then I should tag on a -1 because the partial derivative with respect to z is -1. Have I lost you there?
No.
Okay. And then I'm done basically. So then I just find then the equation is just going to be 2 times, I'm going to dot the gradient. Let's do it right. 2 comma -3 comma -1 dotted with x minus x naught. X naught is -1. That means x plus 1. Comma y minus y naught, y minus 2. Comma z minus, and I don't think I found z, so I gotta find it. We gotta plug in -1. You plug in -1, you get -1 times 4 is -4 minus 2 times -1. So that's plus 2 is -2. And then plus 2 is 0, minus 4 is -4. That's z plus 4 if I did my arithmetic right. Any questions on that? Is that clear so far? Yeah? Okay, and then that is equal to 0. And then the rest is basic dot product. So you get 2, x plus 1, and then plus or minus 3, y minus 2, and then minus z plus 4. Equals 0. Does that answer your question completely?
Yes, it does.
Okay, yeah, so it was a good question because I didn't do an example, and I'm really glad I was able to show you an example because it is an important thing to know, especially for next quarter. It happens in a big way. Okay, so there's our tangent plane using the gradient. And I like to think of not the gradient of f, but the gradient of the function equals 0, where the function of the 3 variables instead of 2. And then you never have to remember any kind of formulas other than the normal vector dotted with a point on the plane is always 0. That's not a formula, that's just a definition of normal vector. And then just use that. Okay, let's go talk about new material. I want to talk about critical points. And hopefully remember a little bit at least, maybe all from first quarter. And I want to give you, I'm just going to give you the kind of standard example that CalPlot3D gives because it works well for us for now. Let's suppose you have a function of 2 variables like this. This is some function that they popped in, and you can do this for any function. Now, can you look at this and visualize that there are 2 maxima? Can you all see that?
Yeah.
Okay, now I want to do something else though. What about the point at the very top? What can you say about that tangent plane at the very top? Yeah, tangent plane is, it's not quite 0, but it has not a 0 number because it's a plane and planes aren't numbers. Does that make sense? Yeah, but you could say it's flat, okay, or parallel to the XY plane. It's probably a better way of saying it. So the tangent plane is parallel to the XY plane. Okay, well, if the tangent plane is parallel to the XY plane, what do you know about the normal vector? What can you say about the normal vector at that point? Where does it point? So if you're parallel, if you have a plane parallel to the XY plane, and you want to look at the normal vector, how does it point?
Doesn't it point orthogonal to the z-plane?
Yeah, I definitely know your thinking is right. Your language isn't so great.
Okay.
So it points parallel to the z-axis. Z is not a plane, it's an axis, right? So it's parallel to the z-axis. So what does that tell you about the gradient? What's the gradient at this maximum? So what's the gradient of this function at the maximum?
It's equal to z?
It's equal to 0.
0. Okay.
Remember that the gradient is a function of x and a vector function of x and y. So not a z. So there's point is you get the 0 vector for the gradient. And if you look at the other max, same thing. Well, now let's take a look at the minimum. So now we can see the minimum. What can you say about the gradient at the minimum? Also the 0 vector. Is that the only point that has a 0 vector for its gradient? Are those the only points? What do you think?
I'm going to say no.
Yeah, the answer is no. Look at the origin here. The origin's the saddle, and that also has a horizontal tangent plane. Okay, or a tangent plane, I'd say parallel to the XY plane. It actually is the XY plane in this case. So it's a lot like when we had one variable calculus. The gradient is our idea of the derivative. And when you wanted to find out where the maximum and minimum were, you set the derivative equal to 0. Do you remember that? And then you said that those might be where the max and min are, but sometimes, like y equals x cubed, you actually get something, you get a critical point, but it's not a max nor a min. Well, the same thing is going to happen when we're talking about functions of 2 variables. But now gradient is going to take the place of derivative. And these are vectors, but everything else is basically the same as soon as you replace that vocabulary. Any questions on kind of the picture and how to see all of this? Okay, I'll tell you, when I was a student, this wasn't even possible. We just memorized formulas and equations, and you couldn't do what I'm doing right now because there were no computers really. So
Visualization wasn't there.
What's that?
The
Yeah,
visualization.
No, there's no visualization unless the instructor, grabbed Play-Doh or something, did that kind of stuff, but nothing like this. So you guys are lucky, and we'll see what the next generation gets. Maybe a chip in their brain or something. So who knows? That's scary, but okay. What I'm hoping for, and I'm actually looking for a grant for it. It'll be too late for you all, I think, because it'll probably take 2 years. Is a virtual reality machine to do this. So you can actually walk through this. That'd be cool. And have you ever seen the virtual reality glasses? So I think it'd be cool to do this with virtual reality. I don't know if y'all agree. Sierra College has one, and that's why I got into it. It's very expensive though. Okay, so case you have, you know, a lot of money to give to the campus. That'd be a nice thing. All right, so now we're ready to go through and do exactly what you did in first quarter calculus. We're going to start out by defining critical point. So a definition. Okay, let f of xy be a function of two variables. Okay. Actually, there's one more thing I want to visualize before we get there. I'm going to change this graph to, let's do a different one. How about x squared plus y squared to the 1/2 or 0.5. Does this one have a minimum? What do you think? Visually, do you see a minimum? Is there a
It
bottom?
appears so.
Yeah, no, this one definitely has a minimum. It's at the origin. Okay. But, and this is just like first quarter calculus, it turns out if you take a derivative of this, you end up with a 1 over root x squared plus y squared in the denominator, or x squared plus y squared, square root of x squared plus y squared in the denominator. And if you plug in 0, 0, you actually get undefined. So this one actually does not have a gradient at the origin, but it does have a minimum. When did you see something like that in first quarter calculus? I'm sure Bruce showed you. Where the derivative was undefined at the minimum. Kind of a famous example, very easy to write out.
Natural log of x?
The natural log of x has never been because that has an asymptote. It's actually easier. It's something that even, you know, 8th graders understand. Okay, should I tell you? Absolute value of x. Do you remember that? That looks like a V. Do you remember that shape?
Yeah.
And the V shape, the derivative is undefined, but it still has a minimum. There's a bottom to a letter V, right? Same thing with this example, is we have a minimum, even though the minimum does not occur when the gradient equals 0, the minimum occurs when the gradient's undefined. Any questions on that? Okay, so I just wanted to visualize it, and that way when I write down the theorem, you'll say, oh yeah, that's what he showed me. So let's let f of xy be a function of two variables. Then I'm going to write AB is a critical point of f of xy. And this is what we're defining, so I'm going to put it in red. If either the gradient at AB equals the 0 vector or is undefined. So do you remember that happening in first quarter calculus, except you didn't use the word gradient, you just said the derivative was 0 or the derivative is undefined. And then we said that f had a critical point. Do you remember that word, those words? Maybe it's too optimistic because it's been a lot of months. Okay, more than a half a year, I think. Or maybe a half a year, something like that. So it's been a long time since you did this. So this is a review of what you already know. But now what we're doing is instead of f of x, we just have two variables instead of one. And I'm not going to write this out, but I'm going to say it. I'm not going to do much with it. And that is that if you have a function of 3 variables, It's the same definition, except you stick a comma z in there. You do ABC, you do 0, 0, 0. But it's the same idea. If you had a function of 10 variables, it's no different. But I'm going to just stick with 2 variables just because it's easier to write. But hopefully, it's no big deal for y'all to extend this to multiple variables. Any questions so far? Okay, now comes the theorem. And this is the same theorem you get in first quarter calculus, except now we have functions of 2 variables. And the theorem is all local maximum, maximum, and minimum occur at critical points. So this is actually word for word the same as what you get first quarter, but the reference is different because now we're talking about functions of 2 variables. But do y'all agree does this feel familiar? Or are your brains like you have no memory of what happened? It wasn't me talking, it was Bruce talking. But do you remember this? That if you want to find a maximum, you take a derivative and you set it equal to 0. You remember that? Or you set it to undefined. Okay. And that's it. Okay. And let me do another theorem. And that is all global maximum and minimum occur either at critical points or, again, this is exactly the same as last quarter, except now I'm like thinking about 2 variables, but I'm actually purposely not writing it, so it should be exactly the same. Where else could they occur? If it's a global max or min. And remember, I know it's been a long time. It's like
at points of discontinuity.
Points of discontinuity are when the gradient is undefined. So that's still a critical point. Is that clear?
Yeah.
Yeah, so we already taken care of that one. Again, this happened first quarter. Origin, not to say origin. Origin, nothing special about the origin because you can shift a function. You could always translate. But it was a good try. Remember?
Endpoints?
Yeah, endpoints. But we need a new word for endpoint because endpoint doesn't really work if you're talking about a XY plane instead of just an x-axis. Does that make sense? So the word we're gonna use, and you've seen this word before, or at the boundary of the domain. So that's a more kind of abstract way of saying endpoints. It allows you to go to 2 dimensions or 3 dimensions. So the idea is a lot of times you say, well, we want to find the global maximum, maybe, on the unit square, right? X and Y between 0 and 1. So what you do is you go and find the critical points. And then you know that the max and min must either occur at a critical point or on the boundary of the unit square. So not the inside of the square, but the square itself, the 2-dimensional square, I guess, or 1-dimensional square. Any questions on that? Any questions? Okay, I'm not going to prove this. And I don't know if any of you, I don't remember, are going to ever see this proof. I forgot, do we have any math majors in the group? Anyone change their mind, want to be a math major? Okay, if not, you'll probably never see the proof. But I will tell you, it starts out with, any guess?
A limit.
Good idea, but let epsilon be greater than 0. which is pretty much how every proof starts in advanced calculus, in what's called. I'm not going to do it. Sound good? Okay, but if you go on and change your mind and decide to be a math major, then you're going to see the proof of this. So right now, you trust me, I don't think it's that surprising that this should be true. Okay, hopefully not, but these are all true. What I will do is give you some examples. Okay, so let's suppose. So and now let's give you a function on insert. Equal x squared minus xy minus 2y plus x minus 1. Okay, any guess what I'm going to ask what the question is going to ask?
What are the max and mins?
Yeah, that's going to be a little later. We're not ready for that yet. But what are the critical points? Find the critical points. Why are we not ready to answer the question, what are the max and mins? Any thoughts? Because it's undefined. This is very defined. This is a polynomial. This is as defined as it gets. So now you got to remember first quarter calculus. What did you also need to decide where the max is? Gradient. You didn't need the gradient in first quarter calculus.
The sign
The sign of the.
point we found, or the coordinate.
You need to find this. You need to use the second derivative test. Do you remember that?
Yeah,
We don't have a second derivative test yet. We will, but we're not there yet.
because the second derivative test told us if it was concave up or down.
Yeah, I told you if you had a max or a min. Remember, and since we're going to be doing something similar, is that if the second derivative was positive, you had a minimum, and if the second derivative was negative, you had a maximum at a critical point. I don't know if you remember that, but that's how it worked. Okay, so right now, let's find the critical points. So the first thing we're going to do is find the gradient. So let's find the gradient. So grad of f. Ooh, is equal to. So what's the first coordinate of the gradient of f?
Fx,
Yeah, which is
2x minus y plus 1.
2x minus y plus 1. Good. Comma, and now the second coordinate. That shouldn't be too hard. It's actually easier than the first coordinate. Yeah, negative x minus 2. Any questions on the gradient? All right, I want to find the critical point. So what do I do?
Set it equal to 0.
Yeah, and note that this sounds weird, but this is not the 0 you're familiar with. This is a different 0. This is the vector 0. Does that make sense? So we're going to set it equal to the vector 0, which is 0, 0. All right. I will let you know what this gives you is 2 equations, 2 unknowns. Because when you set 2 vectors equal to each other, you could set their components equal to each other. And you could say 2x minus y plus 1 equals 0. And negative x minus 2 equals 0. Any questions on that? And I'm going to note something else, and I'm hoping this is obvious to y'all, that is the gradient ever undefined?
It can be.
In this example?
In this example, no.
No. This is a polynomial. Polynomials are as good as they get. Okay, the gradient is perfectly defined. There's no x or y that's going to cause problems with 2x minus y plus 1 or negative x minus 2. But you should always check that. Be conscious of it. Because sometimes the gradient is undefined, and then you got to find those points. Typically, that happens if you have a denominator, and then you have to set the denominator to 0. It also could happen with logarithms or square roots. But this is an example where it isn't. It's fine. Any questions so far? Okay, this is also an example where it's pretty easy to solve. Do y'all agree? What's just right away, what is x? Yeah, x is negative 2. And if x is negative 2, what's y? Can't look at the first equation. Yeah, 3. Good. So we're going to have negative 2. We're going to have 2 times negative 2 minus y plus 1 equals 0. 2 times negative 2 is negative 4. Negative 4 plus 1 is negative 3. So negative 3 minus 1, y equals 0. So y equals negative 3. Any questions on that? Okay, so we now have, we have found our critical point. Do we know whether that's a max, a min, or neither? Because I
We
showed
don't
you
know
in
yet.
the visualization, anything could happen, right?
Yeah, we don't know yet.
Yeah, we don't know. We don't know. Okay, and that's what I was saying. That's why we're not ready to find the max and min, but we are able to find the critical points. Sometimes you get more than one critical point. Often you do. I didn't want to start with an evil problem, but sometimes you do get more than one. Sometimes you get no critical points. That could happen too. This is an example where we got exactly 1. Okay, but you could say, well, all right, we found a critical point, but you shouldn't be satisfied. Okay, that really is not what you care about in the real world. Okay, we want to find out, is this a max or a min? Imagine this at being economics, and you want to find the best strategy that maximizes profit. Should you just go with this one? Cross your
No,
fingers
you
and
want to
hope,
find out.
right? Because the problem is that if it minimizes profit, you actually pick the biggest disaster possible. Does that make sense? So you need to find out, is it max or is it min or is it neither? Okay, it could be a saddle point. So we need our theorem. This theorem is a lot harder to state and probably to understand than the other two that we just did. The other two that we just did, basically I just copied and pasted from first quarter calculus. Okay, here it's got a similar idea, but it's really totally different. So in first quarter calculus, if you wanted to decide if it was a max or a min, what did you do?
Take a second derivative and then plug
Right.
this critical point in.
Exactly. And what's the problem? Why can't we just take a second derivative? What's the issue?
Because we have a vector.
Yeah, because
No.
what is a second derivative? So we need to define a second derivative. Okay, just like when we defined the first derivative as a vector, how many second derivatives are there? There's more than 2, actually. How many second derivatives? There's kind of 2 good answers, but 2 is not it. Okay, yeah, you could say there's 4, and 2 of them are always equal for nice functions. So here's the definition.
And that's because we differentiate by parts, correct?
We
Because we have the
Yeah, but let me just tell you, it's not called by parts. Because remember, by parts we had for integration, so those words mean something different. We use partial differentiation.
That's it, partial differentiation.
Yeah.
Yeah.
Yeah. By parts was that whole thing, UV minus the integral of V to U. Remember that last quarter? That was
Yeah.
by parts. Definitely not doing that. Okay. So what we're going to do is we're going to let f of x comma y be I'm going to write twice differentiable. Function. So that means that we can take all the second order partial derivatives. Then the Hessian of f of xy is, let me do some highlighting because we're defining the Hessian. It's the following. And see if it lets me do it. We'll find out how advanced I can go. Nope, can't do it that way, so I'll do it this way. Actually, it might let me do it. One more idea. Nope. So I gotta go this way. It's f xx, f y xy. Oops, got to insert again. F sub xy. And then I'm gonna write fyx, which is the same as fxy, but I'm just gonna do it for fun. And then f yy. And let me write down the matrix, since it doesn't look that much like a matrix, but it is a matrix. Looks like a table, but a matrix is a table. Okay, so what we're going to do, just like when we had the gradient, we said, well, we can't just write a number, so we're going to make a vector out of it. And now, when you're taking a second derivative, you have to talk about the x derivative and the y derivative, and it could be in any order. So you typically make a table out of it called a matrix. And you've all seen matrices when we did the cross product. So that's the Hessian. Any questions on this definition? Okay, now comes a theorem. And this is called the second derivative test. And it says the following. Let me just copy and paste because it's the same thing. Let f of xy be a twice differentiable function with critical point, or with, I'm going to write gradient of f of a comma b equal the zero vector. So in other words, we got this critical point, and now we want to decide if we have a critical point that's a maximum, or maybe it's a minimum. Or maybe it's a saddle, or maybe we don't know. You remember in first quarter calculus, was there ever a time when you didn't know from the second derivative test whether you had a max or min?
Yeah. If you
Yeah, do
got
you remember when
plus
that
or
happened?
minus,
That was when what?
you got a plus or minus.
Not plus or minus. The hint is neither plus nor minus. And what number is that? 0. Yeah, when the second derivative was 0, then you basically didn't work. Is that clear? Well, it turns out it's going to be a little similar. So I'm going to do the following. And let D, capital D, be the determinant of the Hessian. Okay, and remember the determinant of the Hessian will be fxx, fyy minus fyxy times fyx. But fxy and fyx are equal in all nice functions. So D equals f sub xx times f sub yy minus f sub xy squared. That's the determinant of this Hessian. Is that clear? Okay, then and I'm going to write the theorem out as a table. Okay, not a matrix, by the way. This actually will be a table. Whoa, what just happened? Let's try again.
Will you define what a
I know what
Hessian
happened.
is
It's
again?
down there. The Hessian is this matrix right here.
Okay.
Yeah. So that's the Hessian. The Hessian is this matrix by definition. The
Okay.
matrix of second partial derivatives in this order. Okay. And I know what happened is it cut off on 2 pages, so I need it on 1 page. There we go. Okay, then we have the following. So we have D, F, let's go insert equation, F sub XX, and we have type. So if D is greater than 0 and fxx is also greater than 0, so this is kind of the derivative is positive and the second derivative is positive. Do you remember in first quarter calculus what you said if that happened?
It was a minimum.
Yeah. So we have a minimum. So on the other hand, if D is positive and fxx is negative, put a space there to make it a little pretty. Then we have a maximum. If D is negative, and fxx is anything, in other words, who cares? Then you have a saddle. And what's left? Yeah, if D is 0 and fxx is any, then we don't know. So test fails. So that's the big theorem. That's the second derivative test theorem. It's a lot more complicated because we're talking about 2 variables. There is some extension with 3 variables. We're not doing it in this class. Way too hard. You could do a 3 by 3 matrix. It's just a mess. So I'm not going to do it. We're going to stick with 2 by 2, and that's good enough for first year calculus. Any questions on the big theorem?
Yes, on row 3, where it says D is less than,
We
what
should
is
say
it?
less than 0.
Okay.
Sorry about that. I didn't put the 0 in. Yeah, positive or
Thank you.
negative, basically. Thanks.
Mm.
Okay, any other questions on this? Okay, so let's use it. Let's use it on the one we just did. So here we have our function, x squared minus xy minus 2xy plus x minus 1. And we found a critical point. Now we can decide if it's a max, min, saddle, or we don't know. Is that clear? So let's go find the Hessian. I'll just write H. H is our Hessian. I'm going to insert a table, 2 by 2. Okay. What is fxx? What's fxx?
2.
Yeah, fxx is 2. What's fxy? -1. And that means that's a -1 also. Fyx is always fxy for nice functions. And what is fyy?
-1.
It's not -1. Fyy is 0. Because remember that fy is negative x minus 2. The partial derivative of that with respect to y is 0 because there is no y in that expression.
Gotcha. Mm-hmm.
So now we're ready to find our D. D is the determinant of this matrix. And what is the determinant of this matrix? Yeah, so it's a -1. Let's double check. Yeah, because it's 2 minus -1 times -1, which is just, sorry, 2 times 0 minus -1 times -1, which is -1. And what matters, the punchline for this, for the D, is that this is less than 0. Hopefully you all know that -1 is less than 0. Okay, now again in our table, we have less than 0. So what does that tell us? What do we have? Yeah, we have a saddle point. So that tells you that this function has no max or mins. So f does not have any maximum or minimums. But it does have a saddle point at -3.
Do you mind reminding me of how you find the determinant of a matrice?
So you multiply diagonals and subtract. So it's 2 times 0 minus -1 times -1. Does that make sense?
Yes.
So if you have A, B, C, D, it's AD minus BC is another way of saying it. Okay, and that's a 2 by 2 matrix determinant. Any questions on this example? Any questions? Okay. What time is it? All right, now, by the way, where does this all get hard?
When you
want
have
to say the
math.
facts. Okay,
When
where
you
do you
have
think
the-
this gets hard?
When you have gross functions,
Yeah, and what gets hard about it?
finding critical points, I would say.
Yeah, but in particular, the finding part, again, the whole thing is finding it. The hard part usually is right here, setting it equal to 0 and solving. Imagine if this had like sine of xy plus y and other, e to the xy minus 2x squared plus y squared. You got to set both of those simultaneously equal to 0 and solve. It is brutal. Just let you know that. So I want to tell you that this is an easy example. Okay, but what gets hard is not calculus. What gets hard is algebra, and the algebra could be really horrible. So I picked a nice, easy example instead of a brutal example. Any questions on that?
It blows my mind how that's the case. Like, calculus is, for the most part, pretty straightforward. It's the algebra that ensues afterwards that,
Algebra's tough. Yeah.
yeah.
Finding a derivative is actually not hard at all. I want you to know how to do it. But setting something equal to 0 and solving, that's hard.
Yeah.
So let's take a look at the picture. I'm not sure if I'll copy and paste, but I'll try, see what it does. Yeah, mostly good. Just gotta fix some, and I think that was it. And does it kind of look like a saddle?
Yeah.
Yeah. If I zoom out, I think it'll look more like a saddle. There we go. So there's a picture of our surface. And do you see the saddle? Right there. So it is what we were hoping it was. Okay. Any questions on that? Okay, I'm going to give you a very, very important application, especially to me, because you may think that all I do is teach calculus, but any guess on what it's important for?
Computers.
No, Kristen, I picked on you for a reason. I think only Kristen in the room knows. Any ideas?
Statistics.
No, not economics, statistics. Yeah, statistics. And something you've all kind of seen before, but never actually had any idea how it works. And that is, how do you find the equation of the regression line?
I've always just had Excel do it for me.
Yeah, that works. But if you want to tweak it and do some kind of regression analysis based on some logarithmic curve, then it gets much harder. Okay, but if you understand the theory behind it, you can do it. All right, so let me explain how regression analysis works. Okay, and I'm going to do linear regression analysis, but it works for any kind of regression analysis. Let's suppose you have a bunch of data points. Let's suppose we have 3, 2, 5, 1, and 4, 3. Okay, so what that means is that we have 3 points in the plane, and you want to find the line that fits them best. Any questions on that? All right, so here's the easiest question I'm going to have for you all day. What's the standard equation of a line?
Y equals mx plus b.
Yeah, y equals mx plus b, but for statistics reasons, and for something that's going to come up in 2 weeks, actually, it's better to say a plus bx. So y equals a plus bx. And the reason why you want to write y equals a plus bx is that way you can extend this out and say not just what's the equation of the regression line, but you can say, well, what if you wanted to find the best parabolic fit for points? Then you'd have a plus bx plus cx squared. Or fourth degree, you'd have a plus bx plus cx squared plus dx cubed plus ex to the fourth. So the idea is this sets it up so that you can continue more. All I'm going to do is a simplest example because we only have so much time. So if you have y equals a plus bx, what you want to do is you want to say, well, we have these points, and we want to find the line such that the points are closest to the line. Of all possible lines, we want the distance, and actually we're going to do the square of the distance, so you don't have to deal with the square root, basically. You want the sum of the squares of the distance from the points to the line to be minimal. And that's called the regression line. Again, you've all heard of the regression line, I think so, or best fitting lines, as you'll say. But the question is how do you do it? So here's what we want to do. Well, we say, well, we have these points, and then we're going to say we have this line y equals a plus bx, and I can plug in. So I'm going to plug in 3, 2. When you do that, you get 2 equals a plus b times 3. And if you plug in 5, 1, you get 1 is equal to a plus b times 5. And if you plug in 4, 3, then you get 3 equals a plus b times 4. Any questions on that? Okay, and that's just how you plug in. Okay. So the idea here is that's a y equals mx plus b, right? Now, if we're going to use the line to predict y when we're given an x, we're going to compare the value a plus b times 3 with 2, the value a plus b times 5 with 1, and the value a plus b times 4 with 3. Any questions on that? Okay, now if I looked at this and I said, okay, I got some equations I could just solve. What's the problem? Why can't you just solve for a and b? There's an issue here, a big issue. Right? They're even linear, not even a square involved. What's the problem with saying, now I'm just going to find a and b? I got my equations, I got some unknowns. What's the problem? And there's definitely a problem. Anyone see it? Not all jumping in. How many equations do we have?
3,
How many variables do we have?
2.
Can you solve when you have 3 equations and 2 variables? The answer is no. You get a contradiction. Okay, this can't happen. Does that make sense? So we're not going to be able to solve, but here's what we can do. What we can do instead of solving is we can say, well, instead of saying 2 is equal to a plus b times 3, what we're going to say is that we're going to just guess at some a's and b's. And we see how close it is equal. It's not equal, but maybe how close is it, and want to minimize that distance. Any questions on that? So what we're going to do is instead we're going to look at the distance function, and we're going to call that f of a comma b is equal to, well, we're going to take the square. Actually, yeah, let's just do it. That's what I'm going to do with carrots. So we're going to take 2 minus a minus 3b squared. And then we're going to take plus 1 minus a minus 5b squared. And then we go plus, then we're going to have 3 minus a minus 4b squared. Any questions on what I just did and why? Okay, and the idea is if we got lucky and there really was a solution, then f will just be 0, and that's the best. That means you have no error. So this gives you the error in using the line to approximate the, or to get the best fitting line for the points. And what we want is we want to say among all possible A and B, so kind of y-intercept and slopes, which one is going to give us the best fitting line? So which is going to minimize the sum of the square differences? And how do we do that? Any thoughts? How do you minimize? Yeah, we find the minimum using the first and second derivative tests. Is that clear? Okay, we find the minimum using the first and second derivative test. Now, I'm going to let you know that you actually don't need the second derivative test because this will always result in a unique answer, which is always the minimum. That's theory that I don't have to, I only have like 8 minutes, and that's not enough time to do it. But you can trust me. So what we can do is find the gradient. Grad of f. And, well, that's a vector. So we need to find the gradient, and let's do that. What do you get? So first thing is, let's do this derivative with respect to a first. I know you used to x and y as the variables, but when you're talking about regression analysis, you know, x and y typically are coordinates, so then you got to use a and b for the variables. So it feels a little weird, but it still works. So first thing is, we need to take the derivative with respect to a, of f with respect to a, and notice the derivative of this inside here will be -1. So we're going to have negative, and then we're going to use a chain rule. We're going to have twice times 2 minus a minus 3b. And then we're going to say plus, but it's plus -1, because again, the derivative of the inside here is -1 also. That's minus 2 times 1 minus a minus 5b. And then again, we're going to take the derivative. We get another -1. We take the derivative of negative a. So we get minus. And then we're going to have 2 times 3 minus a minus 4b, comma. Then we're going to do the same thing with the derivative with respect to b. Any questions on this so far? And what I'm going to do, because it's got a lot of the same stuff, I'm going to copy and paste and adjust. Just easier for typing. So now when we take the derivative with respect to b, instead of a -1, we'll have a -3. So that makes this first term a -6. And the rest will be the same. And for this one, instead of a -1, we're going to have a -4. That makes this a -8. And then, oh, sorry, -5. I was one ahead. Here we go. And that makes it a -10 because of this -5b. And then the third one will be the -8. And we set that equal to? So again, we're looking for the minimum. What do we set it equal to?
0.
We set it equal to 0, but it's not the number 0, it's the vector 0, 0. Any questions on that? Okay, so what that does, and I'm gonna go like this and do what I can, copy and paste, so I don't have to keep writing. Is we could set each component equal to 0. So we can set the first component equal to 0. And then we can set the second component equal to 0. Okay, this is kind of messy, but if you had to do this by hand, is this something you couldn't do because there's too much advanced math to do at this point to solve this? Yeah, this is just
No.
2 equations, 2 unknowns, or linear. It's messy. So, but I don't want to waste your time in me like moving around numbers and minus signs and stuff. I will tell you because I did it. In here somewhere. At least I think so. You get 4 minus 0.5x. So A is equal. A is equal to 4, and B is equal to -0.5. So that tells us that the regression line equation is going to be A plus BX, which is 4y equals 4 plus, and then, so that's a minus 0.5x. And that's the equation of the regression line. So I want to mention something. I did this for 3 points. I'll let you know, no one does it for 3 points. People usually do it for, 100 points or something like that. Why did I do it for 3 points?
You were just giving us an example.
Yeah, and take a look how messy it was with 3 points. Imagine it with 100 points. You need a computer program, okay? Excel or whatever you like to use. If you don't use a computer program, good luck. It's not going to happen. I want to mention another thing. Let's suppose you had 100 points. And let's suppose that you didn't want a regression line. Maybe you wanted a regression 4th degree polynomial. Then it's actually very easy to extend this, but your f now is not going to be a plus bx. It's not going to come from a plus bx. It'll come from a plus bx plus cx squared plus dx cubed plus ex to the 4th. But you're going to do the same thing. Then you're going to find your f of a, b. You're going to take the gradient. You're going to set the gradient equal to the 0 vector, okay? And then you're going to solve a big, ugly system of equations, and you'll be able to get all of your letters, okay? And you will use a computer. You would never want to do that by hand. That's the real world. In AI, by the way, what do you think the hardest part is in AI is? When you're doing this regression analysis? Any thoughts? I don't see it, so let me tell you. The hardest part is deciding what degree of polynomial you want. Okay, if you have 1,000 points, you can always choose a 999th degree polynomial. It'd be a perfect fit, but it turns out it doesn't give you the best curve. Okay, so I can't get into it because this is a first year calculus class, but if you decide to go further in this kind of stuff, then there's a lot of depth involved in deciding what kind of curve do you want to use to understand your data in the best possible way. Okay, but you have to understand this whole finding minimums to be able to do it. Okay, because you're going to have to code it if that's what you decide to do. Okay, so it's used in that way. It's used in all kinds of things, but kind of this is a big one right now. Kind of. Okay, any questions at all? I'm looking at the clock and we're about out.
I have a quick question.
I'm going to pause the recording because I don't like to go over if I don't have to, but I'm here to help you guys out.